In our previous presentation, we understood how to find the time complexity of single loops where in the conditional statement we had a function. Now in this lecture, we will understand how to find the time complexity of single loops where in the initialization statement, this time we have a function. A function can be any function. It can be a logarithmic function, an exponential function, or maybe a polynomial function. It can be any function in the initialization statement. So let's get started with this lecture and let's see the topics. The first topic of this lecture is single loop initialization statement with a function. After understanding this topic, we will then proceed with the homework problem of this lecture. Let's start with the first topic, single loop initialization statement with a function. Let's say we want to find the time complexity of this for loop. In this for loop, the initialization statement is I equal to n square. The conditional statement is I greater than or equal to 1. The update statement is I equal to I divide by 2. And within this for loop, we have the printf function with this string Neso Academy. We can observe in this for loop the initialization statement is I equal to n square. This means in the initialization statement, we have a function and the function is n square. This is the polynomial function. Now we need to determine the time complexity of this loop. How do we find the time complexity of a loop? We already learned in our previous lectures the time complexity of a loop is same as the frequency count of the innermost instruction of the loop. The innermost instruction of this for loop is printf Neso Academy. We need to find the frequency count of this instruction, or in other words, we need to find how many times this statement will execute or this instruction will execute. In order to find how many times this instruction will execute, we need to analyze different values of I in each iteration of this for loop. Let's do the analysis now. In the first iteration, the value of I is n square. So this is the value of I in the first iteration. After this, the condition is checked. Can we say n square is greater than or equal to 1? Let's say n square is greater than 1. Then the printf function will execute because the condition is satisfied. And after this, the update statement will execute. According to this update statement, we need to divide I by 2. The current value of I is n square, so we need to divide n square by 2. This is the new value of I, n square by 2. So in the second iteration, we got this value of I, that is n square by 2. Then after this, n square by 2 is compared with 1. Can we say n square by 2 is greater than or equal to 1? Let's assume n square by 2 is greater than 1. Therefore, this condition is true and hence the printf function will be executed. After this, the update statement will execute. Again, we need to divide I by 2. This time we will get n square by 4 because after dividing n square by 2 by 2, we will get n square by 4 as the result. And how do we write 4? We can write 4 as 2 power 2. So the third value of I is n square by 2 square. We can observe a pattern here. The first value of I is n square by 2 power 0 because n square by 2 power 0 is same as n square. The second value of I is n square by 2 power 1. The third value of I is n square by 2 power 2. Clearly, the fourth value of I is n square by 2 power 3. Only the power of 2 is changing. And we can observe the power of 2 is always 1 greater than the previous power. Here we have 2 power 1. So in the next value of I, we will be having 2 power 2. In the next value of I, we will be having 2 power 3. The fifth value of I will be n square by 2 power 4. There is no doubt. This will continue up to, let's say, n square by 2 power k, where k is some value which we don't know yet. but I am assuming n square by 2 power k is equal to 1. I'm assuming this is the last value of I for which this condition is true. N square by 2 power k is equal to 1. This is my assumption. Now we need to find how many times this statement will execute. The answer lies within this series only. In the first iteration, we can observe the value of I is n square by 2 power 0. So in the power of 2, we have 0 in the first iteration. In the second iteration, the power of 2 is 1. In the third iteration, the power of 2 is 2. In the fourth iteration, the power of 2 is 3. We are only looking at the power of 2 because the power of 2 is the only changing factor here in this series. N square is constant. The base 2 is also constant in the denominator. Only the power of 2 is changing. So we are looking at the power of 2 to find the pattern. We can observe that the power of 2 depends upon the iteration number. This is the value of I in the fourth iteration. In the fourth iteration, the power of 2 is 3. So it is clear that the power of 2 is always 1 less than the iteration number. Here also we can observe the same thing. The power of 2 is 2 and the iteration number is 3. The power of 2 is 1 here and the iteration number is 2. So the power of 2 is always 1 less than the iteration number. Clearly, for the last value of I, the iteration number must be k plus 1 because the power of 2 for this value of I is k. As we are assuming this is the last value of I for which this condition is true, therefore, it makes sense that this for loop will execute k plus 1 times. K plus 1 is not only telling us the iteration number for the last value of I, but it is also telling how many times this loop will run. Not only this, it is telling us how many times this statement will run. This statement will run k plus 1 times. Now the problem is we cannot simply write k plus 1 because it will not give us the time complexity. It is good that we found out that this statement will run k plus 1 times. But we now need to represent k in terms of n, which represents the input size. Because the time complexity is always represented in terms of input size. So we now need to represent k also in terms of n. We know n square by 2 power k is equal to 1. This is our assumption. So we have this equation n square by 2 power k equal to 1. Now we need to solve this equation to find the value of k in terms of n. Let's do this now. We can simplify this equation further. We can multiply LHS and RHS by 2 power k. This will remove 2 power k from the denominator in the LHS. And we will get n square in the LHS. And here in the RHS, we will get 2 power k. So we can rewrite this equation as n square equal to 2 power k. Now how do we find the value of k? K is in the power of 2. We can bring this k to the base by taking logarithm on both sides. Now we will take logarithm or log on both sides. Here we have the constant 2. So we can take log base 2 on both sides because log 2 base 2 is 1. This will remove this constant 2. And we know if we apply log base 2 to this value, we will get k in front of logarithm. So logarithm is bringing down the k to the base. That's why we are applying log on both sides. Let's apply log base 2 on both sides of this equation. We will get log n square base 2 equal to log 2 power k base 2. Now in the LHS and in the RHS, we can apply the property of logarithm, which is log a power b base c equal to b times log a base c. Here we have log n square base 2. So a is n, b is 2 and c is 2. Log a power b base c is equal to b times log a base c. So we will get 2 times log n base 2. And in the RHS we will get k times log 2 base 2. So this equation can be rewritten as 2 times log n base 2 equal to k times log 2 base 2. What is log 2 base 2? Log 2 base 2 is 1 because we know the property of logarithm. Log a base a is equal to 1. Log 2 base 2 is also 1. So we will get k times 1 here, which is equal to k. And here we are having 2 times log n base 2. So clearly the value of k is 2 times log n base 2. This is the value of k in terms of n. Now, in place of writing k plus 1 times here, we can write 2 times log n base 2 plus 1 times. This statement will run 2 times log n base 2 plus 1 times. As this is the frequency count of this instruction, therefore the time complexity is theta of log n. This is the time complexity of this loop. We have eliminated the constants and the base. We are getting log n in the asymptotic notation. Here I have mentioned theta because log n is both the worst case and the best case of this loop. This means log n represents both the lower bound and the upper bound of this loop. This is the best case performance of this loop and the worst case performance of this loop. This means this loop must run minimum to minimum log n times. This is the asymptotic value of this for loop. I hope now the concept is clear. Now let's take one more example. This time also we will take the initialization statement with a function. This time the function in the initialization statement is 5 power n. Now we have an exponential function. This is the initialization statement. The conditional statement is I greater than or equal to 5. The update statement is I equal to fifth root of I. We do not have square root, cube root, we have fifth root of I. Now what is the time complexity of this loop? Let's find out. We will follow the same process which we followed for this loop. We now need to analyze this loop by carefully observing different values of I in each iteration. In the first iteration, the value of I is 5 power n because this is the initialization statement and I is initialized to 5 power n. The second value of I is 5 power n whole to the power 1 by 5. Why? Because in the second iteration, I is updated to fifth root of I. And fifth root of I is same as I power 1 by 5. Just like square root of I is same as I power 1 by 2. The current value of I is 5 power n. After updating I to the fifth root of I, we will get 5 power n to the whole power 1 by 5. These two powers can be multiplied. We can write n by 5 also. But I am writing like this, 5 power n to the whole power 1 by 5. The third value of I is 5 power n to the whole power 1 by 5 square. Because this time we took the fifth root of this value of I. And we got this value. This is the value of I in the third iteration. In the fourth iteration, we will get 5 power n to the whole power 1 by 5 power 3. And as we can observe, the only change is in the power of 1 by 5. Each power is 1 greater than the previous power. We can observe a pattern here. This series will continue up to, let's say, 5 power n to the whole power 1 by 5 power k, where k is some value which we don't know yet. And I'm assuming this value of I is equal to 5. This is the last value of I I'm assuming. for which this condition is true. Now let's find how many times this statement will execute. We need to observe this series carefully for this purpose. The first value of I is 5 power n to the whole power 1 by 5 power 0. Here we have to the whole power 1 by 5 power 0. So in the first iteration, the power of 1 by 5 is 0. In the second iteration, we can observe the power of 1 by 5 is 1. In the third iteration, the power of 1 by 5 is 2. In the fourth iteration, the power of 1 by 5 is 3. So one thing is clear, that the power of 1 by 5 depends upon the iteration number, and it is always 1 less than the iteration number. Here the power of 1 by 5 is k, so the iteration number must be k plus 1. So clearly, this loop will run k plus 1 times, and hence this statement will also run k plus 1 times. Now we need to represent k in terms of n, just like we did in the first loop. So let's do this now. We have assumed that 5 power n to the whole power 1 by 5 power k is equal to 5. This is our equation. In place of writing 5 power n to the whole power 1 by 5 power k, I have multiplied these two powers. And that's what I am getting, 5 power n by 5 power k. This is equal to 5. Now we need to find the value of k. For this, we need to bring k to the base, and we know how to do this. We need to take log on both sides. Here we have the constant 5, so we can take log base 5 on both sides. Let's take log base 5 on both sides. We will get log 5 power n by 5 power k base 5 in the LHS of the equation, and log 5 base 5 in the RHS of the equation. Log 5 base 5 is 1, so we'll get 1 here in the RHS. And log 5 power n by 5 power k base 5 is equal to n by 5 power k times log 5 base 5. This is from the property of log a power b base c, which is equal to b times log a base c. So we can rewrite this equation as n by 5 power k times log 5 base 5, and this is equal to log 5 base 5. We know log 5 base 5 from both sides can be cancelled out, or we can write log 5 base 5 as 1. So we can rewrite this equation as n by 5 power k equal to 1. Now we can multiply 5 power k on both sides, so we will get n equal to 5 power k. So n is 5 power k, but we want to find the value of k in terms of n. For this, we need to bring k to the base, and this can be done through logarithm. Let's take log base 5 on both sides because we have the constant 5 here. So now let's apply log base 5 on both sides. We will get log n base 5 in the LHS of the equation, and log 5 power k base 5 in the RHS of the equation. Here we have log n base 5, and here we have log 5 power k base 5. Again, we can apply the same property of logarithm, log a power b base c, which is equal to b times log a base c. So here we will get k times log 5 base 5. So this equation can be rewritten as log n base 5 equal to k. So the value of k is log n base 5. Now the value of k is in terms of n. So this statement will run log n base 5 plus 1 times. And again, this means the time complexity is theta of log n. The best case and the worst case time complexity of this for loop is log n. So with this, I hope it is clear how to find the time complexity of single loops, where in the initialization statement, we have a function. So with this, we are done with this topic. Now let's move to the homework problem of this lecture. Determine the time complexity of the following loops. Let's say these are the loops and your job is to determine the time complexity of these loops. So I want you to solve this problem and I want you to post your answers in the comment section. So we are done with all the topics and we are done with this lecture. Okay friends, this is it for now. Thank you for watching this lecture. I will see you in the next one.